Okay, hello everyone in a new video. So we have reached part 7 of chapter 7, which is the chapter of Newton's second law for grade 11 students. And this one we're going to solve some exercises. Let me start by exercise number 11. So two small blocks of mass m is mass 2 kilograms and mass m kilograms are connected by a light and extensible string. So this is important, which means that tension is being transmitted equally at both ends of the string that passes over a smooth light pulley as shown in the adjacent diagram. This machine is very famous and it's known as the Atul Machine. Now the spheres are released from rest take g is equal to 10 meters per second square. So let's suppose that this is M1 and this is M2. Okay, so M1 is equal to M and M2 is equal to 2 kilograms. Now we have that g is equal to 10 meters per second square, which is the acceleration, which is equal to 10 Newton per kilogram, which means that we are performing this experiment on the surface of Earth. Now the 2 kilogram block moves vertically downwards, traveling 0.8 meters in 2 seconds. Now notice that here, the direction of motion of the block M2 is vertically downward like this, which means that the block M is moving vertically upward like this. They are telling me that the travel distance starting from rest, so v0 is equal to 0, the initial speed, traveling a distance d is equal to 0.8 meters and the duration t is given by 2 seconds. Calculate the acceleration knowing that the motion is uniformly accelerated. So now we need to determine the acceleration. For example, the acceleration can be determined using Newton's second law, but also it can be determined by studying the type of motion. So now let's determine the acceleration by studying the type of motion, which is uniformly accelerated. And now before doing so, let's choose positive x-axis. So we are concerned about M2, so let's choose the positive x-axis to be in the direction of motion like this. Which means that the motion is completely occurring along one axis, which is the x-axis. So let's say, okay, let me here write on the scratch the different equations that we use in uniform rectangle in UVRM. So the equations are given by x is equal to half at squared plus v0t plus x0, v is equal to at plus v0, and a is equal to a constant. So these are for UVRM. I will not write the equations of motions related to URM because we already know that the type of motion is uniformly accelerated. And we are interested in determining the acceleration. Notice that acceleration appears in this equation and in this equation. We don't know the final speed, however we know the distance, which is x minus x0, and we know the time. Then we can use this equation in order to determine the value of a, knowing that it starts from rest. So let me say that since the type of motion is UVRM, which is accelerated, which means varying, then we have x is equal to half at squared plus v0t plus x0, knowing that the distance t is given by x minus x0, which is equal to half at squared plus v0t. Now this is 0 because v0 is equal to 0 starting from rest. So d is equal to half at squared. And we are interested in determining the value of a. So a is given by 2d divided by t squared, the value of d. Now here, no need to distinguish between the components of a and v0 because the motion already exists in one dimension. So 2 multiplied by 0.8 divided by 2 to the power 2. So this is given by, I think, 0.4. So the value of the acceleration is given by 0.4 meter per second square, and that's high. Then the value of A is given by 0.4 meter per second square. Now, if this carry the label x, because we are working in the x along the x component, so you can simply say that A is equal to square root of ax squared plus ay squared. This is 0 because no motion along the y-axis, so A is equal to ax. And why ax is positive? Because it's accelerating in the positive direction that we have chosen. So the value of the acceleration of the system is given by A is equal to 0.4 meter per second square. So notice that this block is accelerating upward by 0.4 meter per second, accelerating downward by 0.4 meter per second square. Okay. Now in number 2, they are telling me draw a free body diagram, show the forces acting on the two blocks. So let me say that this is the pulley. This is the first string. This is the second string. So here we have the first block. And here is the second block. So now I will represent the forces before we choose a reference system. Okay, now you will know why. So as for this block M1, we have the weight which is acting vertically downward like this. I will say it's weight W1. And we have the tension T1 like this. As for the mass M2, it has the weight which is acting vertically downward like this from the center of gravity. This is W2. And we have the tension T2 acting along the string like this, upward. And in this case, recall that T1 is equal to T2 in magnitude because the string is inextensible. Now they are telling me apply Newton's second law to determine the tension in the string. So in this case, because we know the acceleration of both, which is given by A, is equal to 0.4 meter per second square, we can determine Newton's second law for any of the blocks. But notice that in this case, we don't know the value of M1. So here we have two unknowns, T and M. But in this case, we know the value of M and we know the value of the acceleration, so we can determine the only unknown, which is T2. Notice that although the vectorial equation in this case give us two equations, but as for the y component, we don't benefit from it because there are no forces acting along the y direction. So now let's apply Newton's second law. Before applying Newton's second law, let me choose the positive y direction to be downward, which is along the direction of motion. So why? Because simply the block is moving downward. So let me say this is also x, positive x direction, in order for A to be positive. Now let's write the projection of the forces. As for the weight, W2, we have the W2x is given by plus W2, and W2y is 0, no need for W2y. As for the tension T2, we have that T2x is given by minus T2 and T2y is 0. Now we can say that apply Newton's second law for M2. and it's given by sum of forces is equal to M2A. Here we need to be careful that this is the mass related to the block 2. So we have W2 plus T2 is equal to M2A. And now any vectorial equation can be solved by considering the projection along the convenient axis. Recall that here along the y-axis we will not benefit from it. So let's say projection along the x-axis. Simply what will happen here that we'll drop the vector along the vector quantities, and each vector quantity will carry the label x. And we are okay, W2x is given by W2 minus T2 is equal to M2 A. What is A? A is equal to AX, and we have determined this previously to be given by 0.4 meter per second square, which is the acceleration of the system. And we are interested in determining T2. What's the type of this equation? Linear equation or non-unknown. Then after rearranging this equation, then it's given by W2 minus M2A. The value of W2. Now here we expect that the value of T2 must be positive because this direction that we have chosen for T2 is correct. Now W2 is given by M2 multiplied by G minus M2 multiplied by A. Taking M2 as a common factor is G minus A. So T2 is equal to the value of M2, which is given by 2, multiplied by 10 minus 0.4. Plugging this on the calculator, then the value of the tension is given by 19.2 newtons. So T2 is equal to 19.2 newtons. Now they are telling me calculate the value of M. So what does M represent? It's the mass of this block. In order to determine the mass of this block, we need to apply Newton's second law because M appear explicitly in this and the expression. Okay, so now let me say we are in part 4. So let's consider an axis here. Notice that because M is moving upward, so we'll consider the positive direction of the x-axis to be upward and not downward, like this. So here we have that T2 is equal to 19.2 newtons. And let me proceed with this part here. Okay. So we are in part 4. Now let's determine the projection of the forces. We have tension T1. So T1x is given by plus T1 and T1y is equal to 0. Now as for the weight W1, we have that W1x is minus W1, whereas W1y is 0. Now let's say apply Newton's second law. To M1, which is given by sum of forces is equal to M1A. Now the forces that are acting on M1 are given by T1 and W1, which is equal to M1A. Notice that always in order to deal with a vectorial equation we need to consider the projection. So let me say projection So now we drop down the vectors and each vector quantity will carry the label x. Now T1x is given by T1, W1x is given by minus W1 is equal to M1 A. Now notice that here, because the string that we are dealing with is inextensible, so we have that T1 is equal to T2, and A1 is equal to A2 is equal to A, and the reason is given by an extensible string. Okay. Now we are interested in determining the mass. Notice that the mass also appears in the weight, which is given by M1G. So rearranging the expression, then the value of M1 is given by T1 divided by G plus A. Okay. Now the value of T1 is equal to T2 is given by 19.2. The value of G is given by 10 and the value of A by 0.4. Plugging this expression on the calculator, then it's given by 1.85. Everything is expressed in the SI, so 1.85 kilograms. M1 is equal to 1.85 kilograms. And this is reasonable. Why? Because notice that in this case the value of the acceleration is very small, and the difference in the acceleration is due to the difference in the masses. Okay, so always the Atwood machine, the value of the acceleration depends on the difference in the masses, and this we experience in our daily life. Why? If the value of this mass is much greater than the value of this mass, so the acceleration will be very high, so this will fall at a very high rate. But here they are telling you that 0.4 meter per second square, which means that the difference in mass is very small. So the difference in mass in this case is given by 2 minus 1 point, how much? 1.85. So 2 minus 1.85, which is given by 0.15 kilograms. This explains that this must fall at a rate related to this mass. Okay, this difference in mass. So this is it for exercise number 11. Now let me move to the next exercise, which is exercise number 12. Okay, this is also very important. Now this is another case similar to the Atwood machine, but it's not classified as an Atwood machine. Now they are telling me this figure shows a block as sliding. The figure shows a block as the sliding block. So S is the sliding block with mass M is equal to 3 kilograms. Now notice that here they are telling me that S is the sliding block. So S may slide either to the left or to the right, but the reasonable direction is to the right, because S is sliding because it's connected via an extensible string passing through the pulley to H. So H is being pulled downward by gravity or by the weight, so S will be moving to the right and not to the left. The block is free to move along a horizontal frictionless surface such as an air table. So no friction. Here yet they didn't specify how S, if it's sliding or it is at rest. With mass, okay, this block is connected by a cord that wraps over a frictionless pulley to a second block H, the hanging block, with mass M is equal to 2 kilograms. So here they are referring to this mass to be the hanging block and this mass to be the sliding block. The cord and pulley have a negligible masses compared to the pulley. To the block, they are massless, so the cord and the pulley are massless. The hanging block H falls as the sliding block S accelerated to the right. So okay, here they are telling me that H will fall and S will slide to the right, and we have acceleration. So the type of motion of S is UVRM and the type of motion of H is UVRM. Here, although they didn't mention that the chord is inextensible, but here let me say that the chord used is for sure inextensible. Otherwise, this problem cannot be solved. Okay. Number 1, name and represent without scale the external forces acting on S and on H. So let me represent them here, or let me represent them here. Let me start by the forces acting on S. So here we have the support. This is the solid S. So now we need to choose the positive direction of the x-axis. Because it's moving to the right, then we'll take the positive direction to be to the right like this, and this is the positive direction of the y-axis upward. So now, yet we didn't represent the forces. Here we have the weight which is acting vertically downward like this, and we have the tension which is acting horizontally to the right like this, and we have the normal reaction which is acting upward like this, and yet we don't have the force of friction because it's frictionless. This is the weight, this is the tension T, and this is the normal N. Let me say that this is W1, T1, and we don't have a normal for H. Okay, so these are the different forces acting on us. Now let me represent the forces acting on H. So this is the hanging mass. Now because H is falling down, it's convenient to take the positive x direction in the direction of motion, which is downward like this. So this is the positive direction of the x-axis. And therefore, let me represent the forces. We have the weight which is acting vertically downward from the center of gravity like this, and the tension along the cord or along the string which is extensible upward like this. So this is the weight W2 for S, for H, and here we have the tension T2. This is the positive x-axis, and no need to represent the Y because nothing is happening along the Y. Okay, so yes, this is it. Let me say that this is the mass M1 and this is the mass M2. Now in number 2 they are telling me apply Newton's second law of translation to determine the acceleration of S and H. Notice that here in the system there are two unknowns, the tension connecting the two bodies and the acceleration of the system. Okay. However, in this case we can apply sum of forces twice, which will give us 4 equations. But from these 4 equations we will make the use of only 2 because we have chosen the system and to eliminate 2 from these 4, so we are left with 2. Now we need to apply sum of forces separately for S and for H, and we equate it between the tension because the string is inextensible. Then we will determine the value of the acceleration. So we are in number 2 part A. Let's start by the solid S, and let's do the projection of the forces. So as for the force W1, we have that W1x is 0 and W1y is minus W1. As for the normal N, we have N1x is 0 and N1y is plus N1. Sorry, we don't have N, it's simply N. And as for the tension T1, it's given by T1x is equal to plus T1, and T1y is equal to 0. Now let's apply Newton's second law to S. We have that sum of forces is equal to m1a. So this is the hanging mass, the sliding mass. We have the w1 plus n plus t1 is equal to m1a. And recall that in order to deal with vectorial equations, we need to project. Here we'll project along the x-axis in order for t1 to appear in the equation. Now projection along the x-axis, we have the w1x is equal to plus n1x plus t1x is equal to m1ax, and we are interested in determining the expression in terms of t and a. So this is 0 from the above, this is 0, this is t1, and in this case, okay, this is ax. Now let me say the following, that ay is equal to 0, no motion along the y-axis. So in this case, a, which is equal to square root of ax square plus ay square, this is 0, so this is plus or minus ax, so ax is plus or minus a, but since we have chosen a in the positive direction of the x-axis, so we choose the positive value, so simply ax is equal to plus a. So this equation is given by t1 is equal to m1a. And this is reasonable. Why? Because only the acceleration along this sliding block is due to the tension, okay? And no other force exists. If the friction exists, he will have another term which is given by minus half. So now we have applied the Newton's second law to S. So here the expression of T1 in terms of the acceleration is given by m1a. Now we will repeat the same steps but for the hanging mass. We are still in part 2a. So now let me represent the forces acting on the solid H. So we have the W2 axis plus W2 T, okay, W2Y0 as for, okay, this is W vector W2. As for T2, we have that T2x is given by minus T2 and T2Y0 because this is the positive direction of the x-axis. Now let's say apply Newton's second law for H. We have that sum of forces is equal to m2a. m2 represents the mass of the hanging, of the one that is hanging. So here we have that T2 plus W2 is equal to m2a. Now how to deal with vector equations? We need to project. Projection along the x-axis. So we drop down the vector quantity, and each vector quantity will carry the label x. T2x plus W2x is equal to m2ax. T2x is given by minus T2, W2x is given by plus W2, and this is given by m2ax. Now I'm not differentiating between a1 and a2 because I will mention that a1 is equal to a2 is equal to a because the string is inextensible. Now moreover here, let me say that ay is equal to 0, no motion along the y-axis. Moreover, a is equal to square root of ax square plus ay square. This is 0, which means it's plus or minus ax. Ax is equal to plus or minus a. The choice of this direction is in the positive direction, so we'll choose the positive. Then ax is equal to plus a. Then this equation is given by that minus t2 plus w2 is equal to m2a. So these are the two equations that we have determined by applying Newton's second law separately for each of the two masses. And this is reasonable. Why? Because here the acceleration is due to the difference of forces acting on h. W is acting downward and t is acting downward. For this reason here we have a plus sign and a minus sign equated with the acceleration. Okay, now now we need to determine the value of the acceleration. We have two equations into unknown, and let me say that t1 is equal to m1a as well as minus t2 plus w2 is equal to m2a. So how many unknowns we have? We have 1, 2 and 3. This is the same unknown. Here let me say that t1 is equal to t2. The reason is given by an extensible string, as one that a is equal to a1 is equal to a2. So now from the first equation we have t is equal to m1a, and from the second equation we have that t after we rearrange is given by w2 minus m2a. So this is t, not t2. So now t is equal to t, we got that m1a is equal to w2 minus m2a. Here we expect that the value of a must be positive because we have chosen the correct direction. Then the value of a after we arrange is given by w2 divided by m1 plus m2, which is m2 divided by m1 plus m2 multiplied by g. So is this equation reasonable? Yes, because the mass m2, which is causing the acceleration over m1 plus m2, notice that this quantity have no unit because it's the ratio of two masses multiplied by g. So if g has the unit of acceleration, for sure a will have the unit of acceleration because the unit of this is given by 1. Now this is the expression of the acceleration. Now if you are interested in determining the value, then we have that m1 plus m2 is equal to 5. So this is 2 plus 3 multiplied by 10. What about the value of m2? m2 is given by how much? 2. So this is actually 3 plus 2, and this is 2. So it's given by 2 divided by 5 multiplied by 10. So it's 40%. Why 40%? Because this is, sorry, 2 over 5 represents 0.4, so it's 40% of the value of g, which is given by 4 meter per second square. Okay. So the acceleration of the system is given by a is equal to 4 meter per second square, which is 40% of the acceleration. Now they are telling me to determine the magnitude of the tension in the cord. We can use each of these equations that are expressed explicitly in terms of A. So we can say that in part B, T is equal to M1A, which is equal to, what's the value of M1 is given by 3, multiplied by 4, which is equal to 12 newtons, because everything in the SI. And similarly, we can use this expression. So it's given by T is equal to W2 minus M2A. So the value of W2 is given by 20 minus 2 times 4. So 20 minus 8, which is equal to 12 newtons, which is the same as this answer. So T is equal to 12 newtons. Now we are in part 3. Now the system SH was initially at rest, which means that the initial speed of the system is 0. They are talking about which speed, x-axis, y-axis. First of all, for each block, the motion occurs along one dimension, so no need to distinguish between dimensions, and they have the same speed because the system is connected by an extensible cord. And here we have that where h is 2 meters above the ground, so the distance separating the center of mass from the ground is given by 2 meters. So the moment they specify time and distance, we must think about the kinematics, and in particular of these equations that are given by x is equal to half at squared plus v0t plus x0, v is equal to at plus v0, and a is equal to a constant because the type of motion is UVRM. Now they are telling me the time needed by h to reach the ground. We have the distance, we have the acceleration. Time appears explicitly in this equation in terms of distance and acceleration. We cannot use this because we don't know the final speed. So let me say, since the type of motion is UVRM, and the trajectory is rectilinear because it's falling vertically downward, then we can say directly that x is equal to half at squared plus v0t plus x0. Moreover, now we can say that d is equal to half at squared plus v0t, because recall that d is given by x minus x0. We are interested in determining the time. Notice that this is 0 initially at rest. The value of d is given by to be 2. The value of acceleration is given by 4 to the power 2. So simply the value of t squared is given by 1, so t is equal to 1 second, taking the positive solution because time always evolves and it is positive. Now the speed of h as it reaches the ground, so we will use this equation, v is equal to at plus v0. Here you can say that since the type of motion then, so this is 4t plus v0, this is 0, so which is equal to 4 multiplied by the time, which is 1 second. What does this time represent? This time represents the time needed for h to reach the ground, which physically represent the time that you are interested at this instant. You are interested in the speed when h hits the ground. Okay, so that's it for me in this video, guys. In the next part we'll solve also problems or exercises related to the pulley and the Atul machine.